In this video, we're going to talk about the discharging phase of the capacitor, of the transient phases. In a DC circuit, we're going to assume that we have charged up our capacitor, and now we're going to allow that charge to discharge. So just to review a little bit of what we've done before, in the charging phase, we see the following relationships happening. We see that our capacitor voltage starts at a minimum at zero, and over time it goes to its maximum charge. Okay, and that equation looks like 1 minus e to the minus t over tau, where our maximum would be e in this particular circuit. We're looking at this circuit right here. And that tau, remember, we found that by multiplying the resistance of the circuit, or the effective resistance as seen by the capacitor, times the capacitance of the circuit. Okay, so just wanted to refresh your memory on that. For the current in the charging phase, we see that start at a maximum and then go down to 0 over time. And for the resistor voltage, it looks exactly the same. Same shape, because remember, the capacitor current in this case is the same current as the current through the resistor, and those are just related by Ohm's law. So all we would have to do is multiply the current equation by R to get the resistor voltage equation. And it's also going to start at a maximum, in this case E, and go to 0 as well. Okay, so just reminding you of those relationships there before we move on to the discharging phase. Now, in the discharging phase, we are assuming that our capacitor is fully charged. If it were not fully charged, if we only charged up to a portion of its maximum voltage, we would just start the discharging phase from that voltage, and we can talk about that another time as well. But we're going to assume in this case that we're going to fully charge the capacitor and then fully discharge it at the end. So the discharging phase is when we remove our voltage source from the circuit. So our voltage source out here. When we remove that voltage source from the circuit, and when we give the capacitor a path, it can discharge whatever charge is stored on those plates, and it then in turn acts a little bit like a voltage source itself. Okay, so let's look at our circuit here. So the first thing we're asked to do is find the time constant for the charging phase. So you notice our circuit here. We've got a 12-volt source, R1, R2, and a capacitor. So, and we've got 3 different positions for our switch. So in position 1, we would be closing the circuit in this direction. Notice R2 is not really connected to anything, so we'd not have any current through here. So it really doesn't matter that it's there at all. It really doesn't have any bearing on our calculations here. So the charging phase, if you want, we could just draw what that circuit looks like in the charging phase, and it looks like this. Okay, I'm leaving out R2 because R2 is not included in the charging circuit. All right, so the time constant, remember that's R times C. I'm going to say the effective resistance times C. In this case, remember we said in the last video, if you want to find the effective resistance, we would short out the source and we would read the total resistance of the circuit from the position of the capacitor. So in this case, our effective would just be the 20k ohm resistor times the 0.05 microfarad capacitor. So tau in this case would be 1 millisecond. Okay, So that is the time that goes, that's the tau that goes in our equation for the charging phase. Now, the total time to charge that capacitor would be 5 times that. So it would take us 5 milliseconds to charge up that capacitor with this particular circuit. Okay, the next question is to find the time constant for the discharging phase. Sorry about that. I'm not sure what happened here. To find the time constant for the discharging phase. Let's see. We're still here, I think. Okay, so in the discharging phase, that's going to happen when we move the switch, let's say after we have charged our circuit, our capacitor. If we move the switch to position 3, that's going to be our discharging phase. Actually, let me back up and let's talk about this position, switch position 2 for a minute. After I charge this capacitor, if we move that switch to position 2, it's not connected to anything, and it's not connected to the source anymore, so the capacitor can't be charging anymore. And it's not going to connect to anything else in the circuit, so I'm not going to have a path for current. So at that point, at position 2, I guess I should make a note. At switch position 2, 2 V sub C doesn't change. Okay, so basically, if I have allowed enough time for the voltage across the capacitor to charge up to the 12-volt source, or to the 12 volts that it's getting from the source, then when I move it to switch position 2, it's going to retain that 12 volts. If I move to position 2 after I've only charged it up to 6 volts, for instance, then that voltage across the capacitor will stay steady at 6 volts, and so on. So whatever the voltage was right before I open the switch to position 2, that is what the voltage will stay at for V sub C. Okay, so now let's talk about switch position 3. In switch position 3, whatever voltage that cap was when we opened it from position 1, that's the voltage we're starting at with the cap. Now, we have given the cap a path for it to release that charge now. The voltage source is no longer in the circuit, so it's not going to charge the capacitor. Now it's going to allow the capacitor to discharge through the circuit. It basically starts to look like a voltage source at this point. Okay, so let's talk about what, first of all, let's redraw the circuit with switch position 3. I'm going to leave off E because at this point the voltage source really does not impact the circuit at all. So we're going to leave that off. Got 20K and 10K here. R1, R2. Okay, so in this case, we're looking for the time constant for the discharging phase. This was the time constant for the charging phase here. And it might take a different amount of time for the discharging phase. We'll just have to see. So it's still going to be the effective resistance times the capacitance. Capacitance is the same, it's just 0.05 microfarads, but now we've got R2 in the picture. So if we looked at the total resistance of the circuit outside of that capacitor, we'd see R1 and R2 in series. So we're going to take those both and multiply it by our capacitor. So we've got 20K plus 10K times our capacitance of 0.05 microfarads. If we were using proper engineering notation, what would that be? That would be 50 nanofarads, okay? So if we multiply that 30K by 0.05 microfarads, we see that our discharging time constant is 1.5 milliseconds. So what does that tell us? It tells us that if we charge that capacitor, it's going to take us about 5 milliseconds to get it fully charged up to the 12 volts. If we discharge that same capacitor through the discharging circuit, which goes through switch position 3, it's going to take us about 50% longer to do that. Instead of 5 milliseconds, it's going to take us about 7.5 milliseconds. Why is that? It's because we added resistance in our circuit, and that slows down the current. As the current slows down, that slows down the pace at which those electrons are moving back through the circuit, and that slows the discharge phase. Okay, so if you want to slowly discharge a capacitor, you would increase that resistance to do that. All right, so now we're asked to write the mathematical expressions for all the voltage across the capacitor, the current through the capacitor, and the voltage across the resistor in the charging and the discharging phases. Okay, so in this case, let's I'm going to start the charging equations up here. Actually, no, I'm not. I'm not going to do that. I'm going to move, I'm going to stay back down here. So, the charging equations, you can go back and look at previous videos to figure out how we're going to figure this out. But remember the shape, right? V sub c, that's always going to, in the charging phase, start at 0 and go to a maximum value. So that shape is 1 minus e to the minus t over tau. And remember, tau is 1 millisecond, okay? So I'm going to take tau away. Whoops, let me just fix the whole thing here. E to the minus t over 1 millisecond. And what is it going to charge to? Over here is our circuit. When this becomes an open circuit, we're going to see 12 volts across that open circuit. That's going to be the open circuit voltage, and that is what our capacitor is charging to. I sub c, remember that current is always going to start at a maximum and go to 0, which is what the shape of this equation gives us. And what is that current? It's going to be 12 divided by 20,000 ohms. Which is about 600 microamps. Okay, and then the voltage drop across R1 is right here. Remember, it's going to have the same shape that we had for our current. And that's just going to be, in this case, you could just say the 600 microamps times 20K. Or, actually, I'm just going to write this as I sub c times times R1, sorry, times R1. So our 600 microamps times e to the minus t over tau times R1, which is 20k ohms. So that means we're starting at 12 volts and going to 0 in the time it takes our capacitor to charge up to 12. Okay, so now let's, and you can go back to earlier videos and review that. Now let's talk about this discharging phase. What happens after we move the switch to position 3 up here. As soon as we do that, everything in the circuit, in this case, is going to start at a maximum value and go to 0. Okay, so for VC, IC, VR1, and VR2, they all have that e to the minus t over tau, okay, shape. Now remember, for the discharging phase, we had a different tau. So I'm going to change that to the 1.5 milliseconds. And they're all going to have the same shape. We just have to figure out what value they're all starting with in order to write our equations. Okay, so for V sub C, this is really where you want to start. This is what's going to drive everything. When we move this switch to position 3, our capacitor is now going to look like a voltage source, a DC voltage source. Okay, we're going to give it a path to discharge that charge, and it's going to do that in that 5 times tau, or 7.5 milliseconds. So it's not going to be a steady voltage source. It will drop off to 0, but that's what happens when it's discharging. So basically, whatever it charged to, and at that point, that's what it's going to discharge from. Now, we're going to assume in this case that we allowed it to charge all the way up to 12 volts, and we're going to discharge it from 12 volts. Now, what would the current start out as here? Okay, so this is our discharging circuit, and if we're starting with 12 volts here, that's going to drive current in this counterclockwise direction. So right at t equals 0 of the discharge phase, our current is going to be that 12 volts divided by the resistance of the circuit, which is actually 20K plus 10K in this case. Okay, so that is going to be about 400 microamps is where we're starting. So we're going to start at 12 over 10K plus 20K, which is 400 microamps times e to the minus t over 1.5 milliseconds. VR1, to find that, we're just taking that same 400 microamps and multiplying it by whatever R1 was. That was 20K, I believe. So we're looking at 8 volts there to start with. And VR2, that's our 400 microamps times 10K, and there we're looking at 4 volts to start with. Okay, so these are the equations for the discharging phase for the voltage across the cap, the current through the capacitor, the voltage drop across R1 and across R2. Okay, so if we wanted to, so for instance, the charging phase would happen from 0 seconds to about 5 milliseconds, because our tau is 1 millisecond. And remember that it takes about 5 time constants to get to that fully charged state. And then let's say right at the 5 milliseconds we switch to position 2. So that might be 5 milliseconds to whatever 5 milliseconds plus 7.5 milliseconds is. Or 12.5 milliseconds. So this is what's going on. Okay, so if we were to graph that, this is what it would look like. So we would see that in the charging phase, the switch in position 1, we would charge up to our 12 volts there. That's our V sub C. And then as we discharge our voltage, we're going to start at 12 and then drop down to 0 in the, this is not the right drawing. And now that I'm looking at it, that's not the right graph. I think it's for this next problem actually. So it's not drawn exactly correctly, so I'm going to kind of ignore the numbers for right now. And then the current through the capacitor in the charging phase, we're going to see it drop very quickly down to 0. And then in the discharge phase, notice it's dropping on the other side of the axis here and then going to 0 again. Let's look at that. In the charging phase, notice what's going on. I'm going to get rid of this. Okay, so in the charging phase, when we're in switch position 1, our voltage source is determining the direction of the current, which is leaving the positive terminal and returning back to the negative. Okay. However, when we, and this is going to charge up to, let me put it here, this is going to charge up to that 12 volts if we allow it to charge all the way up. Okay, so let's say now we're going to switch to the discharging phase. At this point, this 12 volts over here, this actually becomes something like a source over here that's now going to drive current in the other direction, and that's going to be our 12 volts divided by the 30K, which was the 400 microamps, sorry. So it's going to drive current in the other direction. So when we see this curve, that's what we're talking about. It's in the discharging phase, it drops the other direction. And all that means is it's in the opposite direction of this original current. That's all. It means in the opposite direction. Okay, if we charge again, we see the same start at the maximum and go to 0, and then discharge again, start at the negative maximum and go to 0. The voltage across the resistor, same shape exactly as the current because these are related by Ohm's law. Okay, they're directly proportional, so you're going to see the same graph there. Okay. All right, so working one more example really quickly here. In the charging phase, now the charging circuit is switch position 1. Why? Because in the charging phase, we need a source in the circuit. Okay, so here, V sub C, the shape is going to be 1 minus e to the minus t over tau. Actually, it's not even what it's asking there. It's asking for the time constant. Okay, we'll do that first, and then we'll write the equations. The time constant for the charging phase, remember, is tau. That's the effective resistance times the capacitance. In this case, in switch position 1, all we have is that 2K ohm resistor there times 100 microfarads. So that tells us that we have about 0.2 seconds is our time constant. Okay. Now, the discharging phase happens when we've got the switch in position 2, right here. And tau in that position, again, the effective resistance times the capacitance. So in this case as well, we've just got that 2K ohm resistor and the 100 microfarad capacitor. So again, in the discharging phase, we actually do have the same time constant. So that means it's going to take exactly the same amount of time to discharge the capacitor as it took to charge it. Okay, write the mathematical expressions for all of these in the charging and the discharging phase. So V sub C, I sub C, and V sub R. Okay, so we've got 1 minus e to the minus t over tau for the charging phase, because remember what this says is that we're starting at a maximum and going to 0. I mean, starting at, I said that wrong. We're starting at 0 and going to a maximum value, okay? So that is 1 minus e to the minus t over tau. The current is doing the exact opposite, e to the minus t over tau, which again is the shape where we start at a maximum and go to 0. And the voltage will do exactly what the current, the voltage across the resistor will be doing what the current through the resistor is doing. So now we need to figure out the maximum V sub C, what we're charging to. So in the charging phase, remember that's right here, this capacitor is eventually going to become an open circuit with this not here. So when that happens, we're going to see no more current flowing through the circuit, no voltage drop across the resistor. So we're going to see 8 volts across our capacitor there. I sub C in the charging phase, we're starting with the capacitor looking like a short circuit at that point. So the maximum current there, I'm going to call it I max, is going to be our 8 volts over the 2K. Okay, so 8 volts over 2K, which of course will be our 4 milliamps. And V sub R will be that 4 milliamps times R, which is 2K, which is simply 8 volts. So remember, as the capacitor is going to charge up to 8 volts, the resistor is going to start at 8 volts and go down. So V sub C and V sub R should add up to 8 volts at every point in time during that process. Now the discharging equations. Remember, in the discharge phase, we see that V sub C, I sub C, V sub R, anything in the circuit should be starting at a maximum and going down. Okay, e to the minus t over tau, e to the minus t over tau. Okay, now tau happens to be 0.2 still. We just need to figure out where each of these values is starting. So V sub C in the discharge phase, if we allow that capacitor to charge all the way up to 8 volts, that's where we're going to start. We're going to start at 8 volts and go down to 0. And for I sub C, really we're starting at the same current, right? Because if we're starting at 8 volts here, we've got 8 volts across 2K ohms of resistance. So we're going to start at the 4 milliamps and go down to 0 from there. And what about the voltage drop across that resistor? It's going to be that same 4 milliamps, this time times the 2K, which is also 8 volts. I'm going to put parentheses around there. 8 e to the minus t over 0.2. Okay, and so those are your discharging equations. If you want to plug in values of time, you'll see kind of where you can find the voltage across a capacitor or the resistor or the current through both at any given point in time. And these, of course, would be the graphs that would describe what you saw going on here. Okay. All right. One final note: if you have multiple capacitors in the circuit in series, you're going to combine capacitors in series just like you did parallel resistors. Okay. And for capacitors in parallel, they're going to add just like the total resistance of series resistors. Okay, so here we're going to have the total capacitance, CT equals 1 over C1 plus 1 over C2 plus 1 over C3, and in parallel, we would just simply add them together. So if I'm looking for the total capacitance of this network here, I'm going to start out here and combine the 3 and the 3 microfarad and the 6 microfarad in series, and I'm going to combine those like this. Okay, so and I'll call that maybe CA, 1 over 3 microfarad plus 1 over 6 microfarad. So CA total would be 2 microfarads. And that would be, so if I were to redraw this with the 2 microfarads at the end, this is kind of like reduce and return that we did with series parallel circuits. So then we've got 2 microfarads, 4 and 6. All of these are now in parallel because they share 2 points in common. So CT would simply be this, the sum of all of them, or 12 microfarads. Okay, so if you have multiple capacitors in your circuit, you would combine them the opposite way you combined resistors. So this concludes the video on the discharging phase of the capacitor circuit and how to combine resistors. Watch the previous videos if you need to review the charging phase, and we will work more on steady state next time.